Okay, good morning. First chapter, we review some fundamentals we learned from trigonometry and signals and systems. First one discuss some trigonometry, and we review several important identities that we are going to use in this class. The first one is sine 2 theta, and that one equals to sine theta times cosine theta. The second one is cosine 2 theta. That one will be equals 1 minus 2 sine squared theta equals also equals 2 cosine squared theta minus 1. And the next important is 2 cosine alpha times cosine beta equal to cosine alpha plus beta plus cosine alpha minus beta. Those are from trigonometries, but in electrical engineering technology, and those alpha, beta, theta are physics. For example, the first application for this is if we let alpha equals omega 1 times t. Omega is the angular frequency, t is the time. Alpha is in math it is an angle, but in communications this one is the phase. Right? So alpha equals omega 1 times t, and beta equals omega 2 times t, another frequency. Can be the same, can be different. Then from here, this formula, if we have two signals, the first one is cosine omega 1 t times the second sinusoidal function cosine omega 2 t, and based on here, we move this 2 to the right hand side, it will be equals to half cosine alpha plus beta means omega 1 plus omega 2 times t, omega 1 plus omega 2 times t, and plus half cosine omega 1 minus omega 2 times t. Now if we implement this in physics, if we have this multiplier, multiplication, that means this multiplier. Then if we have two input, the first one is cosine function, cosine omega 1 t. The second one is cosine omega 2 t. These two signals multiply together, and the output will have this and have this signal. Suppose omega 1 and omega 2 are a little bit different, but very close. Then we can see omega 1 plus omega 2 very close to, suppose omega 1 approximately equals omega 2, we let this one equals omega, and these two add up together, they almost equals 2 omega. So this one close to 2 omega, but this part very close to 0. That means this one is a very high frequency, almost double the frequency here, and this one will be equal to 0. That means this is the low frequency, this is the high frequency. Now look at this operator, multiplication. And we state that this operation, this is a multiplier, is nonlinear. Nonlinear operator. The reason is we have a new frequency generated. At the input we have frequency omega 1 and we have frequency omega 2. And at the output we have a new frequency and we have another new frequency. And this, because the new frequency generated, so this is nonlinear. Nonlinear means, recall that when we study AC circuit, operational amplifiers, if we have an amplifier, suppose this is the system here, and this is the input, this is the output. If the gain equals A, what does that mean? That means if we have input VIN, then the output VO will be equal to A times VIN. We never mention about the frequency. That means the frequency here will be the same. For example, in phasor representation, you said this is 10 with some angle, for example, 30 degrees. 10 is the voltage. Then suppose this one equals 20, the gain equals 20. After this, then we are going to have 200, this one times this, then with angle 30 degrees, or if this one has another angle, for example, 10 degrees, that's possible, right? Okay, then this one will be 30 plus 10, so equals 40 degrees. We mentioned the amplitude, we mentioned the phase, but we never mentioned the frequency. So what is the relationship between the frequency of the input and the output? They must be identical. No matter what frequency here is, then we have the same frequency. 60 Hz, 60 Hz, 1 meg, 1 meg. So that means we do not have any new frequency generated. So this is a linear device, right? So this is called a linear amplifier. But for this, it's different. This one is non-linear device. We have a new frequency generated. So if we say V in times A, then equals V out, we cannot use a phasor representation because the frequency can be different. Right, those are the circuit analysis, but in communications, we do not call this a amplifier. Instead, we call this a modulator, right? Called modulator. And we are going to discuss the technical details later time. As we mentioned in the very beginning, modulator is almost the same as demodulator. There's only one little difference. It's a filter followed by this. Again, we discuss this later. Anyway, modulator, both modulator and demodulator are nothing but just a multiplier. As we said, in all this equipment here, we are looking for multiplier to be used as modulator and demodulator. Alright, so this is so you can see theoretically we just use a trigonometry identity, and we technically we just to implement, for example, how to implement this modulator and demodulator, that means how to implement this multiplier. We may have a lot of schemes to implement physically in the lab. The multiplier, we can use linear amplifiers, we can use logarithmic amplifiers, or a lot of things we are going to discuss in the next chapter. But here, what you need to know is modulator, demodulator is nothing, just a multiplier. We can prove this in theory with trigonometry identity. So that's the first. A special case is if omega 1 equals omega 2. So this is the first one. The second one is if omega 1 equals omega 2, and we assume these two are equals omega, then this one times this will be equals omega t, cosine omega t squared. So omega 1 equals omega 2. So these two multiply together equals cosine omega t squared. So this will equal to this one, omega 1 equals omega 2, so that will be half cosine 2 omega t, then plus this minus this equal to 0, cosine 0 equals 1, and this one equals half. So this is totally DC, and this one is doubles the frequency from the original input. If we use a low pass filter, and we use a low pass filter, this part after the output, this part will be gone because this is a high frequency. What we have is only this part. Now the interesting thing is if we have another signal MT at the front, then this one will be here also MT, and this one here will be also MT. Assume MT can be a AC signal with lower frequency. Then after the low pass filter, we can see we have this one. So that means we can extract this signal from here. That process is called demodulation. Again, we are going to discuss the technical details of demodulation in the next chapter. Okay? From here, you see modulator, demodulator, all the same, just multiply. And we use there are special example of trigonometry identity. Another example is not related to communication, but is very useful in also, and we can compare that with this one. We see the difference between modulator and that one. Okay. The other one is we are not listed here, but still identity is cosine omega 1, cosine omega 1 t plus cosine omega 2 t. So instead of multiplier, we just use addition. Addition here. From actually, if you look at this, that is this way. From the right hand side, go to the left hand side, and this one equals 2 cosine omega 1 minus omega 2 over 2 times cosine omega 1 plus omega 2 half then times t. This is also identical. We go this way or we go this way, so they are the same. And we go from the right hand side to the left hand side, we get this one. Now look at this. What is the physical meaning for this formula? Again, instead of this angles, we use sinusoidal functions. So one cosine function signal plus another cosine signal, that equals 2 cosine, the difference, half of the difference, omega t here, then times the cosine, half of the average of the frequency, then times t. Let's consider another special case. If these two frequencies are very close, omega 1 not equal to omega 2, but very close, then omega 1 minus omega 2 will be very close to 0. That means this one is very close to 1, but not exactly 1. It's still a function of time. But it's slowly changing. The change is very slow, just like this. Close to 1, but not. And this part is high frequency. The frequency is almost equal to the original frequency. If you play guitars, if we have these two strings here, we know the frequency of these two strings adjacent are very close, the frequency, right? And if you play these two at the same time, that means we have this one, frequency omega 1, and we have this one. If you strike this, you just generate a cosine function. And this frequency, one is omega 1, another one is omega 2. They are close, so frequency is almost the same. Now, these two signals, you play this together, so that's, to our ears, you hear this, the addition of these two signals, add up together. Not multiplication, just add up together. What do you expect when you hear these two together? Now look at this. Suppose this one equals omega plus a delta omega, and this one equals omega minus a delta omega. This one is very small, right? Just, for example, if this one equals 900K, this one equals 1100K, so this one we can write 1000 minus 100. This one will be equal to 1000 plus 100. So this is the delta, this one is the omega. Right? So here, this is the difference divided by 2 is just this 100. So the first one is cosine omega, cosine 100 t. The second part is multiplied by cosine, this to 8 divided by 2, so that equals 1000 t. And these two signals multiply together. And we know this one is very small. This is just for explanation. So in real life, this one may be even smaller. Okay, so for example, equals only 1 frequency. This one equals 1000. If you look at only this is just the cosine function like this. If this one equals 1 here, that means the amplitude equals 1, so it's just like this. This is 1 here. But for this one, for this multiplication, this one serves as the amplitude. This amplitude close to 1, but not equal to 1. So that means this amplitude will change will vary with the respect, like in cosine function behavior. So what does that mean? You hear the sum of these two, actually you hear the tone of this one, cosine 1000t. But this one serves as an amplitude. The amplitude is no longer a constant, it varies with time. Anyone play guitar before? You can try to hear these two together. You see it's different. It's not two signals. Sometimes it looks like just, this is called a beat. The strength will change. The strength, this is the amplitude. The strength changes in a sinusoidal way. It's not a constant, not just one sound. The strength not is constant. It's like this. You can try. Even if you do not play, you can find one. Just strike these two at the same time. Try to find the difference. Okay, but anyway, let me ask: is this one is a nonlinear operator? That means input, output. Do we have a new frequency generated? Input y is equal to omega 1, the other one is omega 2. Looks like we have this new frequency, this new frequency. My question is, do we really have new frequencies? Okay, no. From a Fourier transform or Laplace transform, we know this one we have this frequency equals omega 1, this frequency equals omega 2, no problem. But this one, because this is multiply omega t times omega t, their frequency, the spectrum of this multiplication is not equal to this and this. If you want to find the spectrum of this multiplication, we still need to go this way. So that means the spectrum of this still equals this. So there are no new frequencies generated. So this addition is linear-wise. It's not nonlinear. So addition cannot be used to change the signal frequency. Only multiplication here. So this is the difference between the addition and multiplication. We are going to have a homework problem. Let you to practice to see more clearly the difference between these two operators. Okay, any questions on this? Good? The second is average of a signal. When signal here, special case is a sinusoidal function. So the first one is the average. We know we take the integral of a signal. So for example, cosine omega t plus initial phase theta here, then dt, and this one for cosine function that equals the same thing for sine function, omega t plus theta, dt. If we do the integration, then we divide by constant t, and we know this one will be equal to 0. The physical meaning for this is any cosine or sine signal, sinusoidal signals have no DC component, because the average of a signal gives us the DC component of the signal. The average of both signals, cosine function, sine function equals 0. That means no matter cosine function or sine function, they have no DC component. We already know this. For example, can you charge your DC battery directly from this the power, AC power from the source? No, you cannot. How do you charge your battery? How do you make a battery charger? And we already know you cannot directly plug this AC to your battery, because we know, like this here, half cycle is positive and half cycle is negative. So this one here is charge your battery, then this one will discharge your battery. So your battery just back and forth oscillates, you do not charge any. So how to charge your battery? And when I believe we discussed this in other lower level classes, how to make a battery charger. we know this part will charge your battery, but this one will discharge. One easier consideration is, okay, we remove this half cycle, then we charge, we stop, then the next cycle here, right? Again, this one is gone here, and this one charge. Okay, so that means we charge, stop, charge, stop. That is the rectifier. This is called half-wave rectifier because we do not have this half-wave, we do not have this half-wave. So this is a half-wave rectifier. Then if we use this one, we can charge battery. The charge, stop, let's go. So how to implement this? It's very simple, right? So we have this AC, like in the wall. Now you just use a diode here, then this is your battery. As easy as this. Half positive cycle, we pass this, the current will charge your battery. The next half cycle, this one will open, right? Current won't flow this way, so it's open just like this, no current. Then you hold your charge, then until the next half cycle will charge. So this is called half-wave rectifier. Right? Half-wave rectifier, we can do that, but the efficiency is low. Instead, we may use a four-wave rectifier. That means this one will go up again, this one will go up again. So we can charge during both half cycles. Right? Now we need to use, instead of half wave, you need a four wave. So you still remember how to implement that circuit? If you want to use this, you need to use transformers. Right? Or you can use a four diode, then you don't need to use a transformer. Right? But anyway, it's not the purpose for us to discuss the rectifier here. Anyway, the point here is if we have this, take the absolute value, the rectifier in electrical engineering equivalent to absolute value in mathematics. So we just take the absolute value. We keep the positive, we inverse the negative into positive. So this here. Then dt, the same thing to this. If we take the absolute value, and we know this one will equal to 2 over pi. 2 over pi equals like very close to 70%. 2 over 3, so like less than this, but approximately equals this one. This means the output of the rectifier will equal to around 60 to 70% of the amplitude of the input. And by this relationship, when you design battery charger, you need to choose the input amplitude correctly, and based on what kind of battery you want to charge, 12 volt or 1.5 volt or 3.7 volt. So you choose the input AC voltage, and based on this relationship. Okay, again, we don't discuss the details. This I assume you already know this, so this is just a recall. Alright, another one is how about we make this squared? Right? So cosine squared omega t plus theta. Recall this one before. This is called the demodulation process. Cosine squared. For this, and the same thing applies to here. And this one equals, it's easy to do the math. That one equals half. This is the mathematical derivation. We are going to use this conclusion in demodulation process. So we just need to memorize this thing equals half. Right? This is easy to understand, right? Because the cosine squared equals 1 plus cosine 2 omega t plus theta divided by 2 this. Right? So this one equals 1 over t, this one here, right, dt. We know this one is just the half, that is the dc. The dc integration divided by the length, this one still equals half. But this one, look here, this is a cosine function. Even a higher frequency than this, so it's double the higher frequency. So for this one cycle, actually for this signal, it is 2 cycles. 2 cycles, the period can still equals t half t or something. So that means this one still equals 0. So the integration, the average of the second part equals 0, the first part equals half. So we add up together, still equals half. That's how we get this result. All right. Next concept is called orthogonality. Anyone knows this before? Orthogonal means perpendicular to each other, right? When we discuss 2 vectors, it's these 2 vectors are perpendicular to each other. If 2 vectors perpendicular to each other, so A, right? We use V1, V2, better. Vector V1, vector V2, these 2 will be equal to 0. So one is V1 like this. So this is V1, this is V2. Vector means we have amplitude, length, side, and we also have direction. This is in vector analysis. We know this dot means this means equals V1, the amplitude times V2, the amplitude times the cosine, the angle between these 2. In this example, this is 90 degrees here, because it's perpendicular to each other. And this one, cosine 90 degrees, definitely equal to 0. So if 2 vectors are perpendicular to each other, the dot product equal to 0. In this class, we don't discuss vectors, instead we discuss signals or functions. We claim 2 functions, fx and gx are orthogonal to each other. The definition is fx times gx, and from some domain, from some region, from A to B, and if this integration equal to 0, then we call these 2 are orthogonal to each other. And we write as this f dot g, and this one equal to 0. So these 2 signals are orthogonal to each other. Again, this is math. We don't want to discuss the details here. Instead, we apply this one to our class. So suppose fx equals a sine function, sine m omega t, and this gx equals cosine n omega t. Let's see, we use cosine first. Both are cosine. Cosine m omega t, this is cosine n omega t. Omega here is a frequency. M, both m and n are integer. So this is harmonic signal, this is a harmonic signal. If we calculate this, cosine m omega t times cosine n omega t, and do integration from one period and divide by t and dt, we are going to find out if m equal to n, this is back to cosine squared m omega t. So this one will be equal to equals half. Equals half, not equal to 0. How about f not equal to n? If m not equal to n, then this one equals 0. Again, we discuss the physics. That means if you have 2 sinusoidal functions that they have different frequency, then they are orthogonal to each other. That means if you multiply these 2, integrate with in one period, then divide by t, that time it will be equal to 0. If this times sine function, this is sine function, we have the same result here. But if we have a sine function m omega t times the cosine n omega t dt, then no matter what the relationship between m and n is always equal to 0. Why this is useful? Again, you will already know this. I mean, in electrical engineering. For example, let me ask. Suppose I have a sinusoidal function like this one, cosine 10t. Apply this to a load R, suppose unit equals 1. What is the power on the load? You know this from a AC circuit. This is the cosine omega t. That's just the cosine sinusoidal signal. We apply this as a source to the load. The load resistance equals 1 ohm. What is the power on the load? So that's P. So for V1 equals cosine 10t, P1 equals V squared over R divided by 2, right? Because this is DC. Sorry, this is AC. So this V squared, this V1 is 1 squared over 2 times 1, right? So that equals half. We know this, right? Alright, now another one. Suppose we remove this signal and we have another signal here only. This is V1, so V2 equals 2 cosine, for example, 100t. That's different. If we don't have this one, we only have this. Again, what is the power for this one? V2 equals 2 cosine 100t. What is the power of V2? When we calculate the AC power, we don't care about the frequency, right? We only care because it's only V squared over 2R. That's all. We never mentioned about the frequency. Right, so this one will be equals 2 squared, the amplitude squared, then divided by 2 times 1, so that one will be equals 2. That is what we learned before. Now, if we add these two signals together, V as V1 plus V2. These two add up this together. What is the power? What do you think? Should we add these two powers together? Just like that? So half plus 2 equals 2.5. Is that correct? We used this before, right? But let's, from the definition, the power equals, we know, so V squared divided by R. V squared divided by R, then T like this, dt. Here, that is the definition. This one is definitely correct. This one is based on our experience. This one is correct. So let's plug this one into here. Let's do this. Okay, so this one equals 1 over t, 0 from t. Okay, V equals these two add up together. So equals cosine 10t plus 2 cosine 100t squared dt, like this. And look at this. Let me continue this. So equals 1 over t here. This one will be equals x plus y squared equals x squared plus y squared plus 2x times y, right? Algebra. Right, so that's equals cosine t squared plus the second term is 2 cosine 100t squared. Okay, we have another term because 2 times cosine 10t times 2 cosine 100t. Right, we have another term here. And all this together, then dt here. Okay, now look at this one. This part, cosine squared dt, give us the power of the first part. So this part equals a half. And this one here give us the second power, as P2. How about this one? We need to have this term here from math. But based on our experience, the power is only this term plus this term. We totally ignore this term. Is there anything wrong here? No, because this cosine 10t, cosine 100T, they have different frequencies. That means M equals, for example, equals 10. This M, N equals 100. If M and N are not equal, they are orthogonal. That means they don't have any power. So the power here equals to 0. So that means our experience is good. We don't need to consider the cross product part. We only need to consider this because they are orthogonal to each other. Any question on that? So we can still keep using this idea. Again, if you have another source here, then the total power will be the power 1 plus power 2 plus power 3. What rule is this? Superposition? Superposition, right? We mentioned this before, superposition. And keep in mind, superposition only works for linear circuit. If you have a square or something, that won't going to work. Only for linear circuit. Okay. Not important concept is Euler's identity. Identity. Anyone knows this? I believe you know this from when we discuss trigonometry or phasor analysis. E to the j theta to the power of j theta equals cosine theta plus j times j theta. And from here, we know e to negative j theta will be equals to cosine theta minus j sin theta. And if we add these two together, then we are going to get cosine theta equals, add up these two together, so equals half e to the j theta plus e to the negative j theta. And sin theta will be equals to e to the j theta minus e to the negative j theta, then divided by 2j. So these two pairs are equivalent. In a special case, e to the j 90 degrees. What is this? E to the j 90 degrees. Cosine 90 degrees equals 0, and sin 90 degrees equals 1. So this one just equals j. How this is useful? Why this one is useful? How we can utilize this? If you have, for example, input signal, and if you just multiply by j to this, that means you are going to change the phase of the input by only 90 degrees. You add 90 degrees phase to the input. So this is called 90-degree phase shifter. Okay. So you multiply by j, that means you add a 90-degree phase to it. We try to relate the math and also the engineering technology here. Okay. If you have a circuit, you claim that you can shift the phase by 90 degrees. It's a phase shifter. Everybody knows that, right? Phase shifter. Then, mathematically, you just multiply this one by a j. What is j? j here is square root of -1, right? Definition. Anyone still remember this?
Mathematically, it's usually I, but in engineering,
Yes,
we use
because
J
we reserve
because-
I for current.
Right.
So that's why, right? So mathematically, in math, they use I, but here we use J. Although J is also a unit, it's called current density, but more frequently we use I for current. So that's why we use J for this. Look at this. This one is an exponential form. This one is a complex form. We have this real part, this is the imaginary part. Right? Again, we know we do not just discuss math in this class. We want to use this math as a tool for our analysis. Right? So we know cosine theta. In this class, we said this is cosine omega t. We like this signal, right? So this one will be equals to the real part. This one equals the real part of this, right? So equals the real part of E j omega t. That is what we are going to use in this class. We do not discuss this, play with all this math, but we use this one as tool. So cosine function, if you are good at cosine function, you can consider this cosine function as the real part of an exponential signal. Why bother? I'll give you this. Why you want to use this one? Well, this exponential function is more popular than this one. A lot of applications is much easier to use this one instead of this. For example, what is if you have a differentiator here? So this one is just a differentiator. We know how to implement a differentiator in circuit, right? Have you learned any? Differentiation, integrator. This one is supposed to be in 311. Operational amplifiers. So this is differentiator. If your input is cosine omega t, what is your output? Your output will be equals negative omega times sine omega t. Make sense? Right, now you look at the input and the output. The looks are different. This is cosine function, this is sine function. So it's not easy to represent the output with the input. But how about this? If we have this here, it is same circuit, and instead of the cosine function, we use this one, e to the j omega t. E to the j omega t, take the differentiation, what is it? And now we need to recall math. E to the ax differentiation, what's this? It's still e ax, right? But there's an a constant here. Right? So this one means, look at here, take differentiation e to the x here. So it will be equal to e to the x here. Then there's an a here, so that one will be j omega. Now look at this, compare this input and this output. What is this? This one is equals j omega times your input. So this is the input here. If we represent your input with the exponential signal, then the output for this differentiator is just j omega times your input. And this one is obvious, but here is not that obvious. Cosine function differentiation equals negative omega sine j omega sine omega t. Right? So that's why we use this one. Easier. Right? So we know the concept of transfer function, right? Transfer function is defined by the output over the input of the system. Right? For this, what is the transfer function for here? Right? The output divided by the input, so equals just j omega. So the transfer function is just the j omega. This is different. So next time you see j times omega, you know that is a differentiator. So it's much easier than to use the exponential instead of cosine or sine function. This one is not that straightforward. This one is.
You said the transfer function is what?
Transfer function is defined by the output divided by the input. Okay? Are you taking 311 or 312 right now or last semester?
311.
311? Okay. So this transfer function. This idea is very important. No matter if you discuss circuit analysis, control systems, a lot of things, transfer function is always. That means it's output divided by the input. For example, linear amplifier, the gain equals 100 or equals 20 dB. So we know output over the input. And that is special because the frequencies are the same. So 100 cosine omega t over cosine omega t equals 100. That is the gain is constant. But in general, that is called transfer function. Basically, we have 4 types of transfer functions. Because the input can be voltage, can be current. The output can be voltage, can be current. So we can use output voltage over input voltage. That is what we know before as the gain of this amplifier. We can use the output current over the input current. That's called current gain. We can use the output voltage divided by the input current. That is called the unit is ohm. Still transfer function. Or we can use the output current divided by the input voltage. So the system like this. This is in, this is out. This one can be voltage, the output can be voltage. And this one can be current, this one can be current also. So this one over this, and that is the gain, voltage gain. This one over this is the current gain. This one over this is in terms of the unit is the resistance, voltage over current. Or this one over this is the conductance. But anyway, we have 4 types of transfer function. The Euro transfer function we mentioned is just the voltage over voltage. So next time you see, and we keep in mind we are going to use these ideas later time. So I hope you can remember this. J omega as the transfer function means this system is a differentiator. Alright, let's move further away. What do you expect the transfer function for integrator? Differentiator is times j omega. What is the integrator? Okay, 1 over j omega. 1 over j omega. So every time you see divided by j omega, that is the integrator. So very, very neat. The key here is every time when we want to deal with the cosine function, we don't need to use the cosine function. Instead, we prefer not to use cosine function. Instead, we just use the exponential. For example, you give me this, I don't use this. I assume you give me this, but only the real part. Then I use this one as the input to do all the calculations, do the analysis. At the last step, I just take the real part, then that is your result. Because when we calculate E, exponentials is much easier, much faster than cosine function. We are going to use these ideas later time when we discuss the spectrum of FM signal, frequency modulated signal. We need to use these ideas to solve that problem. Okay, any questions on this? A lot of things, right? But again, we focus on the ideas. So later time you are going to see this, why we want to use this. All the practices, all the tricks, all the methods we use have foundations. That means are correct. We can use this. So later time when we said, okay, instead of this, we use this, you know, this is good. Next is the power of a signal. First, I will discuss the energy of signal. If we are given a signal, a cosine function, a sine function special, we already know that. But here, it's a complex signal in general, ft. How to find the power? The energy first. The energy equals do the integration from all time and ft times ft complex conjugate. What is a complex conjugate? This star. Right? For example, 3 plus 4j, that's a complex number, right? What is the complex conjugate for this one? 3 minus 4j, right? We keep the real part and we reverse the sign of the negative of the imaginary. So that's minus 4j. Right? So that is called complex conjugate. If two signals are, if a signal is real, for example 3, plus 0j, that is a real number. Then complex conjugate here, 3 minus 0j, 3 plus 0j, 3 minus 0, that's the same thing. So that means for real signal, this complex conjugate will just equal to this for real signal, because there's no imaginary part. So for real, that one will be equal to this from here to here, then ft squared dt. Now we know when this ft equals a cosine function, so when ft equals v times cosine omega t, that is what we learned in circuit analysis, in AC circuit analysis. So that one will be equal to here will be equals this to here, the v squared cosine squared omega t then dt. Okay. So that is only a special case of the information. Sixth is the power. The power is related to energy, right? So power is defined by the energy per unit time. Right? This power P will be equal to 1 over T, then from 0 to T, and F times complex conjugate dt. This part is the energy, right? With some period, and then divide by T. Okay. So this works for periodic signal. But in general, this signal may not necessarily be periodic. It can be arbitrary. In that case, we still consider there's a period, but that period equals infinity. So we just take the limit, t goes to infinity. Right? If your signal is not periodic, then you just take those very long time, right? But t goes to infinity. So no matter how long it is, I just consider it as one period.
So when do we take the limit?
The limit means if your signal is not periodic. For example, if your signal like this, here, periodic signal, then you just from here 0 to t, then you do the integration of this part, then you divide by t, that's it. Right? Because this t is limited. But if your signal is like this, for example, here, like this, it's not periodic. But we can still consider this one as periodic from 0 to t, but this t goes to infinity, can be very long. So you do the integration from here to here, then you divide it by t. But that t is just very large. If a signal has a limited energy, that is called an energy signal. Energy signal. Energy signal if E is limited, right? Is limited by A, is bounded. And power signal, if this power is less than A is less than infinity, so this one less than infinity. It's a constant. It's less than a constant. Right, let's discuss, for example, thermal noise. When we analyze circuit systems, communication systems, thermal noise is always there. Do you think thermal noise is a power signal? Is the power limited? The power is limited, right? The thermal noise, the power just like a very small as responded. How about the energy? The energy of the thermal noise, right? That is not limited. That can be as large as we want if your time is long as long. For example, your radio receiver inside has a thermal noise. Right? If you consider the total energy from now to tomorrow this time, right? You have energy. If the day after tomorrow, 2 days, then the energy will double. Okay, 1 week later, 1 year later, so as you can take as long as you want. That means the energy can be as large as you want. So thermal noise is not energy signal. Instead, it is a power signal. The power is limited. You cannot make the thermal noise power as large as you want.
So you're saying that thermal noise is a power signal?
Yeah, the power is limited.
What is an example of energy signal?
Energy signal, for example, if you have band limited, if you have time limited signal, like this, if your signal is goes to 0 at some time, no matter how long this, it goes to 0. Then this one is, because we can do the integration, we can always find, this one can be very large, but it's always bounded. It can be 1 million, can be 1 billion, and no matter what, because we stop at some time, so it will be bounded. For example, atomic bomb, that we know the energy is very large, right? The energy is bounded. Once it's gone, then it's gone. No more energy. And no more energy. So that is bounded. But if you keep going, for example, the sound, suppose the life of the sound is infinity, suppose, okay? Then the energy can be as large as you want. You have 1 year, 1 year, okay? But in real life, also, the sound has life. So that is also energy signal. It's bounded. Sometimes this concept has only meaning for theoretical. Right? For example, here we know the power of the thermal noise. Later time we are going to learn this. The power of the thermal noise equals KTB. Right? KT times B. B is the bandwidth. Right? You have a receiver, you have a cell phone, you have bandwidth, right? So it's 10 meg or no matter what. And T is the temperature in Kelvin. The operating temperature. For example, here in this room, maybe 300 K. Right? And K is Boltzmann constant. It's a very small constant, but it's a constant. So we can calculate the thermal noise power. And we know your temperature cannot be very high. Your bandwidth is also limited. Then this power is bounded. So it's power. But the energy E is power times T. Although this is bounded, is less than some constant. If your T goes to infinity, then this E can go to infinity. So this is not energy signal. Instead, it is a power signal. Alright, next we are going to discuss some another important concept, 7, right? Trigonometry, Fourier series of periodic signal. In 323, we mentioned we didn't do a lot of Fourier transform. Instead, we focus on Laplace transform. They are very similar. Laplace transform is more general than Fourier transform. We mentioned that. Again, here we do not discuss the details how to calculate the Fourier transform, or we only use several examples that will be very useful in this class. The definition is if we have a time domain signal ft, we can represent this signal with a trigonometric Fourier series. And the first part is the DC component. The signal in general will have a DC component. Then plus we have infinite terms n equals 1 to infinity an times cosine n omega t. Those are the cosine terms. And sometimes we are going to have n equal to 1 infinity and bn times sine n omega t and sine terms. We have a formula to do this. For example, a equals t and 0 to t and ft times dt. So this is the DC component for this one. And how to calculate an, the coefficient. The an is 2 over t, and from 0 to t, and ft times cosine n omega, then dt. And omega t here. And bn will be equals to 2 over t, 0 to t, and ft times sine n omega t, then dt. Do the integration, then divide by 2t. So you can see here, a1 equals this ft times cosine 1 omega t, and a2 equals this thing ft times cosine 2 omega t, and all this do the integration, then divided by times 2 over t, and bn is the same thing. So if we are given the time domain signal ft, we can easily calculate all the coefficients. So this is called Fourier transform, or trigonometric Fourier series. The one example we are going to use a lot in this class is this thing. So this is 0, like this. This is called a rectangle pulse train. Rectangle pulses, like a train. They are series of all this. So it's rectangle pulse train. And we plug this signal, this is ft, into these formulas, and we can easily calculate all these coefficients. And the important part is we list all these coefficients, so later time we can use this. So omega t, we say omega t, so wt. So wt in time domain can be equals to, if, let's make some assumption, if the duty cycle equals 50%, what is duty cycle? Duty cycle means, for example, we start from here, this one and this will be the same. So this is called the duty cycle, right? Duty cycle is this duty divided by the cycle. The duty part divided by the cycle. So in this case, if this one 1, 0, 1, 0, 1, 0, all the same, the duty cycle will be equals 50%. Suppose the duty cycle equals 50%, then and if the height equals 1, what is the DC component here? This equals this, this equals this, this equals this, and this height equals 1. What is the DC? DC is just make it the average. So the average of 1 and 0 equals half, right? The average of 1 and 0 equals half. So the DC component A0 here, if you do this, integration, then divide by t, that equals half. And then plus all these coefficients calculated from here. I won't bother you how to calculate this. If we start the origin, start time from here, right in here, we know this signal is symmetric. Right? So you can see this one flipping into this way, they are symmetric. If the signal is symmetric, that means that we don't have any thin function. Thin function, because this is an even function, an even signal. Thin function is odd. Right? So the cosine function look like this. See, they are even. They are symmetric. But the thin function, like this, look at this signal. They are anti-symmetric. So if your signal here is even, we cannot have any component like this. We can only have a signal like this. Right? Yes, it is correct. So in this case, it will be 2 over pi. The first term is cosine omega 0t. The next one will be equals minus 1/3 cosine 3 omega 0t, then plus 1/5 cosine 5 omega 0t, then minus 1/7, and so on. So that's a lot, infinite terms. You may ask, what is omega 0? Well, omega 0 times this t. What is t? T is the period of the time domain signal. That one equals 2 pi. So if you give me this t, then I can easily calculate this omega 0.
Are all of these omegas like the second?
This one?
The 1/3 cosine.
3 omega 0.
Okay.
This one 1/5 cosine 5 omega 0.
Okay.
Then next one is minus 1/7. You can see the signs are alternate, and this 5 omega 0. The next one will be 7 omega 0, and so on. The reason is because of this configuration it is even, so we do not any thin functions. If we start here, if we start from here, look at this, or we start from here. No, we start from here. So you see, we are going to have, instead of a cosine function, we are going to have all thin functions. We know cosine function and thin function, just 90-degree phase shift. They are the same thing, right? If you look at the oscilloscope, can you tell me is this cosine function or thin function? You cannot. Cosine function and thin function are the same. We just different starting point. They are 90-degree phase shift. So they are the same thing. I would like you to understand this. Again, you look at this signal, and next time you look at this signal, you will be, you are going to see, okay, these two are the same. So next time you look at this rectangle position, instead of this rectangle pulses, you see there are a lot of cosine or thin functions. How come? Look at this. The first term is DC. It is this one. It's half this, right? Okay, the next term is cosine this. So you will see this one will be equal to like this, and here like this. Right? If I said, okay, give me only one term of this rectangle position, that is this one. So this one is approximated by this. At least the DC is good, right? I said, okay, it looks like this one is not accurate enough. You give me two terms, this term and this term. Then this term will be like this. So you are going to use these first two terms to approximate the original. So look, the first term is this, the second term is this. So you add these two together, you just shift this one up by half. So that means if your rectangle pulse train looks like this, what you approximate with the first two terms, you look like this. Right? The first term is only constant. The second term is a cosine function. You say, your rectangle pulse train is like this. Have you ever seen this before? Yes. When you transmit 1, 0, 1, 0, 1, 0 with some system, if your system bandwidth is very low, then, for example, on the oscilloscope, you see you have a rise time, you have a fall time. That signal is no longer ideal rectangle anymore. It is just like this. Why? Because look, you cut off all the high frequencies here. You only take the DC and the lower frequency. That means your system has a limited bandwidth. So that is correct. Now, how about if you want to increase your bandwidth a little more? That means your system is a little bit better than this. You take the first three terms. The first three terms, you add another one. In this case, you are going to have like a better, so maybe like this. Like this. So it's, okay, your original rectangle pulse train looks like this. See, it's better, right? The rise time is smaller, the drop time, the fall time is also smaller, so it's better. Why? Because your bandwidth is a little bit wider. Now you can see if you have infinite bandwidth, that means you can recover all the bandwidth, then all these terms add up together must be exactly equal to the original rectangle pulse train. But in real life, do we have a system that has infinite bandwidth? No way, right? That means when you transmit this rectangle pulse train, when you receive it from a system or from a channel, communication channel, anything, you never get exact 90 degree up, 90 degree down. You always have something like this rise time and fall time. You always have not ideal. The reason is because you have a limited bandwidth. This idea, again, is important. For example, now most of the communication systems are digital. Digital means you transmit 1, 0, 1, 0, 1, 0. If your system is ultra wide bandwidth, you transmit 1, 0, 1, 0 perfectly like this, then I can make this pulses very narrow because it's up, down very fast and perfect. So I can still distinguish this 1, 0, 1, 0, 1, 0. So that means I can transmit the data very fast. So the data rate is higher. But if your bandwidth is limited, when you transmit this, you are going to slowly up. When you transmit 0, you're going slowly down. Before you're going down, because see, this is the pulse like this. But when the pulse is down, but you still need some time to fall. Now, before, if this one, after my second one, now you will mess up. So if your system is not ideal, then you cannot transmit this 1, 0, 1, 0 very fast. So your transmit rate is limited. So this gives us ideas how to choose the system. If your bandwidth is wider, then your signals can be transmitted very fast. If you're slower, then you cannot. That's why when you watch HD TVs, high definition movies, you want your bandwidth to be as high as possible. Otherwise, you mess up. So you can see all these can be explained from here. You don't even need to test. You don't need to test. We already know this from 301 or something. And when we discuss the electric digital signals 1, 0, 1, 0, you know when you generate from the oscilloscope, they never rise 90 degrees or fall 90 degrees. That's why we introduced the rise time and the fall time. If you look at the oscilloscope, they have a bandwidth. Some oscilloscope has a bandwidth of 500 meg, some has 100 meg. If you compare two oscilloscope or spectral analyzer, no matter what, if the bandwidth is smaller, then the signal will be worse compared to the other. So now we know the fact and we know how to explain this. Later time when you design or you choose a communication system, you know how to do this. Okay, any other questions? Okay, we are going to stop here and we continue next time. All right, thank you.